let's explore another elimination reaction. And this one is called the Hofmann Elimination. So, the special nature of Hofmann eliminations are that they form the anti-Zaitsev product. Now, we'll need to start from an amine, and we'll choose an amine that will give us an option to either deprotonate here and form the terminal alkene, or deprotonate here and form the internal one. Now, the Zaitsev product would deprotonate and form the internal alkene, but the Hofmann reaction will deprotonate on the less substituted portion of the molecule. And we're going to go over why. Now, we have several steps here. First step is to alkylate this amine. So we're going to do several SN2 reactions on this amine to form our bulky leaving group. We're going to need quite a bit of this, so we're going to put in an excess amount of our methyl iodide. That's going to completely methylate our nitrogen up here and prepare it to be a bulkier leaving group. Next, we're going to add silver oxide and water This will convert the iodide into a hydroxide. So it's going to exchange the ions in the solution by precipitating silver iodide, and it will leave behind hydroxide. That hydroxide will then be used in conjunction with heating the reaction to form the elimination product. Which in this case is the anti-Zaitsev product. Or you may also call this the Hofmann product because we're doing Hofmann elimination. Now, how does this mechanism work? Well, first step, we'll need to alkylate the nitrogen up here. I have some videos on that, but briefly, we'll just cover one of these reactions. So we have attack there. This is an SN2. Then we're going to form this intermediate. Now we've added a carbon group here. And as I talked about before, we don't stop with just one carbon because now this is even more nucleophilic as soon as we deprotonate. So we'll just use a little bit more of this nitrogen base we have in the solution. Come in, deprotonate. And we'll need to do this 2 more times. And if we do that, of course we've got some iodine hanging around here somewhere. We'll repeat it a couple more times, and we're going to get the fully alkylated nitrogen. It's going to have a plus charge on it. And then we'll have our iodide here. Now, next step is to add the silver oxide. And the silver oxide will convert the iodide here into hydroxide ions. Now, you may have somebody just say, it's going to do that, and not explain how that happens. So I'm going to just briefly explain that process. We have silver oxide, and if you have water, it's actually in equilibrium. I should draw a big arrow going back this way because the equilibrium definitely lies with the reactants in this case. But it makes silver hydroxide here in the solution. Now, this is favored almost 1,000 times over this one, but what will then happen is we've got some silver plus ions. Got some hydroxide here. The iodine will precipitate with the silver. Hydroxide ions get formed in the solution. So now, what we have in the solution, arrow backwards, is this. And I'm going to go ahead and draw in one of the protons that we're going to deprotonate here. And now we have hydroxide from the silver oxide. That's going to come up here, take that proton, and we're going to do our E2 reaction. And we will form our leaving group here. It's going to be the nitrogen that's been alkylated, and our Hofmann Elimination product, and some water from the base, taking the proton. And of course, we'll also have silver iodide precipitating out of the solution. And that precipitation is going to remove silver from this side of the equation, drive this equilibrium forward so the reaction happens in a reasonably timely manner. And then, of course, we'll also be heating it to help promote this. Now, you might say, well, why does this happen in the anti-Zaitsev product? Because we have hydroxide, and generally when we put hydroxide in a solution, we would expect it to deprotonate here. Well, there is a reason why we bulked up this leaving group, and that's to promote the Hofmann product. So to explain this, it's probably best to bring in a model kit. So here's this reagent right here. It's ready to be deprotonated. Now, remember, if we're going to go E2, which this process does, we have to have the leaving group in the anti-position from the hydrogen that's going to be taken. So, in this case, I've got the longer chain here, and either this proton or that proton would need to be taken in order to form the double bond internal and make the Zaitsev product. So let's see why that's not very favored. So when we line this up in the anti-position, you'll notice that there's this group right here. That's this carbon at the end. And if we look at this bulky nitrogen, alkylated nitrogen up here now that we've alkylated it, you'll notice it's bumping in to this carbon, the rest of the carbon chain here. And let's see what would happen if we move the other proton into position, right? Same thing. Our groups up here are bumping into each other. So it's really not going to want to be in this position because of the steric hindrance right here. So what's much more favored is this position, because now the hydrogens are facing this bulky group, and that just opens up the sterics a lot better. Now, over here, where we have hydrogens all the way around, any one of these hydrogens could be eliminated, and you'll notice that we have less steric bulk here interacting with our product. So this is much easier to position in the orientation that it needs to be in order for this to be removed and our E2 mechanism to eliminate over this bond right here. So that's why the Hofmann elimination is selective towards the less substituted portion, right? Just because of steric hindrance. So this is an effective tool to form the other product and eliminate on the less substituted carbons. And again, sterics is the reason why.